In this video, I'd like to discuss how to properly detoxify the ultra-heavy toxic metals that would be things like gadolinium and uranium at the bottom of the periodic table. As a matter of fact, if you're watching this rather than just listening to it, I suggest you open up in a separate window an image of the periodic table of elements. That way you can look at the elements as we're discussing them and see where they fall in the periodic chart. Okay, so broadly speaking, I divide toxic metals into four classes. The first class I call the simple toxic metals, and those would be things like aluminum, nickel, cadmium, barium, arsenic, and lead. And for these, EDTA is an excellent chelator. EDTA stands for ethylene diamine tetraacetic acid. That's a fancy way of saying 4 vinegar groups. And it's the vinegar groups that grab on and attach to the toxic metals. And we carry a suppository that contains EDTA. It's called metacardium, and that might be of use for you. The next class of toxic metals are things I call conditionally toxic metals. These would include chromium, iron, and calcium. These aren't toxic in of themselves, but they can become toxic either by the form they're in or the amount that we take. As an example, we need chromium. It helps regulate blood sugar, but we need it in the trivalent form. And if it gets in the hexavalent form, it's toxic. The same with iron. We need ferrous iron, that's Fe2, but ferric iron, Fe3, is toxic. Now, unlike chromium and iron, calcium doesn't have a toxic form per se, but as we age, we accumulate more and more calcium in our tissue, and that becomes a problem. So calcium in the kidneys is kidney stones, and the gallbladder is gallstones, but it also shows up in the joints as arthritis, in the arteries as arteriosclerosis, in the breast and the prostate and the brain. Calcium appears everywhere. We do turn to stone as we get older. So EDTA is also useful for these conditionally toxic metals, chromium and iron, but in order to remove calcium, you have to use a specific type of EDTA. That EDTA can't have calcium already bound to it, and most of the chelators that I see out there that are using EDTA are using a calcium-based EDTA. If you want to pull calcium out of the tissue, you have to have a calcium-free EDTA. We use a magnesium and potassium EDTA in our metacardium. So if you're looking at working on calcium, make sure you're getting a calcium-free EDTA. The third class of metals is mercury. It's by itself. And the issue with mercury is something called redistribution. So let's say you have mercury someplace innocuous like your abdominal fat. It's certainly not good to have it in your body, but your body has, through its wisdom, sequestered it someplace away from the internal organs in the brain. And then you take a chelator that grabs onto mercury, but not completely. It only half grabs onto it. And as it pulls it out of the abdominal fat, that mercury chelator combination, that compound, bumps into something that the chelator wants more than the mercury. Now the mercury bounces off, and it might bounce off and go someplace worse, like the brain or the spinal cord or along a nerve ending. And that's what redistribution of a toxin is. It goes someplace worse than where it started. So if you are dealing with mercury toxicity, feel free to call us for a consultation. There's a very specific way to do it. And if you do it improperly, you can end up doing more harm than just leaving where it is. That's that would be the third class of toxins. And then the fourth class of toxins are the ones that I really want to get into in this talk. And that is the ultra heavy toxic metals. And if you look at the bottom 2 rows of the periodic chart, those are the lanthanides and the actinides. And these include things like gadolinium and uranium and thorium. So one whole section of those are all radioactive. And the trouble with these particular metals is they're so large that it's hard for most chelators to get a good grip on them. And I'll explain in a moment why that's a problem again. So there are some 40 million MRIs done every year in the US. 1/3 of these inject a contrast agent in order to make a clearer image for the radiologist, and what they use is gadolinium. Now, the trouble with that is 6 of the 7 gadolinium contrast agents are poorly designed, and they release gadolinium into the patient. They don't all get excreted. If someone has weak kidneys, or they had a soda before the injection and boosted up their phosphorus, either of those things will make them more likely to have gadolinium deposit into their tissue. The weak kidneys, because the contrast agent is spending more time in the body before it's flushed out, and the soda, because the phosphorus in the soda, the phosphoric acid, can displace the gadolinium off the chelator and let it deposit in the tissues. Now, there's 4 things to know about a chelator: the shape, the type of chemical bond, the number of bonds it makes, and the size of the chelator itself. In terms of shape, we have linear chelators and macrocyclic. Linear chelators are like ribbons that get tied around something, and macrocyclic, which means big circle, are like claws that grab onto something. Now, claws are more stable than ribbons, so we want the macrocyclic chelators. In terms of bonds, we have ionic versus non-ionic. Ionic bonds are more stable than non-ionic bonds. In terms of the number of bonds, also called the coordinate number, the more the better. And in terms of the size, we want to make sure that the chelator is large enough to contain and wrap around the metal in question. So in the case of gadolinium contrast agents, only one of them uses an ionic macrocyclic chelator. That means 6 of the 7 of them have a tendency towards releasing gadolinium into the patient. And again, this is even more a problem if they have weak kidney function or have high phosphorus in their bloodstream. The phosphorus will displace the gadolinium 3 times faster than normal. Now, in terms of uranium, many people have uranium in their drinking water if they drink water from a well. If there's radon in your area, well, radon is a breakdown product of uranium, so that's an indication you're probably having uranium in your soil, and if you have well water in your well water. Now, gadolinium is known to cause a variety of symptoms: digestive problems, headaches, brain fog, lowering of IQ, hearing and eye problems, pain, itching, burning, tingling, prickling, deep bone pain, pain in the joints and in the head. Feelings of electricity, muscle twitching, weakness, ear, nose, and throat problems, body temperature issues, hair loss, balance problems, swelling. It's a very toxic metal, and definitely something you don't want in the body. Uranium and thorium, well, they're both radioactive, and they also cause terrible symptoms. One giveaway is when the teeth start to disintegrate. Both uranium and thorium will displace calcium in the bones and the teeth, and then now you have something radioactive in your bones and teeth, and the person ends up with accelerated osteoporosis and tooth loss. You know, there are, of course, other toxic elements at the bottom of the chart. There's lanthanum, which is found in swimming pools and drinking water. Cerium is found in flints of lighters and self-cleaning ovens and catalytic converters. Samarium is in recycled plastic. Dysprosium is in wind turbines and electric cars. Erbium is found in sunglasses and cheap jewelry. Ytterbium is found in stainless steel cookware, and luteum is found in gasoline and diesel. So what do we do about these toxic metals at the bottom of the periodic chart? Most chelators aren't going to work with them. Most chelators aren't big enough to grab onto them. So it's sort of like if you have a smaller atom, you can think of it this way. If you have a baseball in your hand, you can grab it and hold on to it pretty well. But if you try to grab onto a basketball with your hand, you probably won't make a very firm grip with it, and it can get knocked out easier. So what we want is a macrocyclic chelator, the claw and not the ribbon. We want something ionic for stronger bonding. We want a large number of coordinate bonds so it can grab onto it in lots of different places, but we need to make sure it's large enough to physically grab on and not let it loose. The other aspect of it being large enough and having enough coordinate bonds is you want to completely wrap around these toxic metals, because even a toxic metal that's chelated, if it's not fully chelated, can cause some damage on the way out. And the more you wrap around it, the less reactive it is. So the less side effects you have as it's leaving the body. So even a toxic metal being removed is also a challenge, hard on the kidneys if you don't have the right chelator. So the chelator that meets all these specifications is called DOTA. It's macrocyclic, It can make ionic bonds with gadolinium and uranium. It has 8 coordinate bonds and is large enough to wrap around these toxic metals. It's sort of like the big brother from EDTA. It's very similar to EDTA, it's just stretched out a little bit more. If you're interested, we do make a product called Captamet, which contains DOTA in a liposomal form for optimal absorption. One of the challenges is a lot of these metals aren't tested for in most alternative medical tests. So even if you've had a hair analysis or a urine challenge test, you might have metals that simply aren't showing up on the test in these lanthanide and actinide series. So if you have ever had a MRI with contrast agent, or you've been exposed to some of these rare metals, you might consider our Captamet product.